Hi, it's very good to see that everybody didn't leave as soon as you start to have a Geology 101 class. Let's see, I also want to acknowledge that Dr. Dars is in the room with us today. We have, as subsurface geologists, been looking at subsurface geology of South Louisiana for basically our whole careers, and we use data sets that allow us to predict whether or not faults might come to the surface, and we know that they appear to. And that's really, why we are very grateful that we got funding to support some graduate student work, bringing, basically the subsurface analysis up to the surface. Let's see, make sure I know how to do this. Nope. What did I do? It's this, right?
Yes.
Okay.
Use this button right here.
Sorry, okay. So, the first thing to note is that the greatest risk that we have from faulting is not from earthquakes. Although there have been some felt reports, they're very small and they tend not to, cause great disruption. The first manifestation that you might see from a surface fault is that you see a deterioration maybe in a marsh, or you might see river offsets. You might see offset on either side of a fault trace at the surface. Next, people would look at near surface, and you might look at sediment core transects and see that there might be some thickening of different sediment patterns on the downthrown side versus the upthrown side. You might go in and look at high resolution seismic data. Seismic is just bouncing sound off of layers in the earth, and we can do it both shallow and deep. You also might see some offset of a river channel or things like that in the subsurface. But really best would be to have a view where you could look much deeper in the ground and then project it up so that then you can do more focused work near the surface. So we have the ability in Louisiana, we've got a great deal of energy industry coverage of the subsurface using 2D and 3D seismic data. And that's part of what our project is working on. And I just wanted to emphasize that faulting patterns that have been in place for millions of years didn't just happen 40 million years ago. Those processes are continuing today. And part of what we're trying to do is get this information to the forefront so we can see exactly how it is affecting the transportation infrastructure in Louisiana. All of these risks are going to vary depending on their location and the types of infrastructure. Basically, you have a fault trace that's going to be a line, and it's going to intersect a line if you're dealing with a road or railroad or bridge or dam or something like that. All right, so just a real brief review of what happens with a fault. In South Louisiana, we've got a slippery surface down below. Sometimes it's salt. Actual halite that was deposited early in the opening of the Gulf of Mexico. Other times it's clays. And these can be at 20,000 feet. It provides, let's see, is that how I do the, yeah, okay. It provides a layer down here that these faults end up slipping on. And an important aspect is when the surface center and then it tapers off to the side. And if we jump real quick into what a subsurface picture of South Louisiana might look like, this is a transect from Valentine, Louisiana, and then it kind of goes through Terrebonne Bay and it ends up out, at the end of the, like Timberleer Island. And then this one goes from basically the Leeville area kind of all the way to Fouchon. In this diagram, you've got these straight little peg things. Those are oil wells or gas wells. You've got horizons that are mapped. We've got pink is salt. It started way down here, and it's been mobilized, and it moves up because it's low density and buoyant relative to the sediments. And the salt provides a sliding surface that these arcuate-type faults have slid on the salt. And you can see that in some places we've got huge bodies of salt that are as large as Mount Rainier, but buried to great depths in South Louisiana. I included this diagram right here. Oh, this is 1996, sorry. I included this diagram because I wanted you to see that there is some patterns that we can recognize. So once we start bringing this and understand faulting patterns, we'll be able to make predictive models as to what their effects may be. So why is this important to transportation infrastructure? This is a really famous fault that was identified. This is Highway 11 bridge. This is actually going towards New Orleans from Slidell, and it's about a 4-inch bump. I mean, if you travel this road, you feel it in your car. And this was identified by this fellow, John Lopez, who's now head of the Lake Pontchartrain Basin Foundation, and he rode it every day because he had a camp on the North Shore. And in the mid-90s, early to mid-90s, the USGS started doing some 2D seismic in Lake Pontchartrain. And he may have also had access to other data, but basically he thought he'd see whether or not there was anything going on down there, because as geologists we think subsurface. And subsequently a chirp profile was made, and this fault was identified as impacting the surface pretty much right where the bridge crosses it. If we take a look, just going back to Geology 101, that first layer was laid down as a horizontal layer, okay? And we're just going to kind of run through an animation here. At this point, that first layer is offset by about 10 feet, and it's only at 40 feet. At the time that layer B was laid down, of course, this is all laid down horizontal and connected when it was laid down to begin with, and then offset with time. That fault D, layer D is now about 20 feet displaced, and so on and so forth until we get to the point where we have layers at the top that obscure the scarp itself because sedimentation is active, and you can see that there's a great deal more sediment on the downthrown side. This is the sort of thing that a geologist is looking for, to know that this is an active fault at the surface. Now, if this continues, of course, you end up with a bridge that's got a bump in it, and that bump is just a little line where that fault impacted it. Now, if we continue, so that's one way. We had seismic, we had deep seismic that then allowed us to focus some shallow, expensive, but shallow seismic on the surface, and concentrate on exactly where we were. Then we were able to identify that fault. But in other places, we really are just dealing with kind of a surface manifestation. So this is kind of a famous example. This is down here. This is Buras right here, and we're right in here. This is a Cuvion USGS diagram that shows basically color ranges are showing you when land loss was observed, and most of this land loss was, a lot of the land loss was observed in the 70s. This is the sea level curve right here, and it's showing that Grand Isle, which is the red curve up here on the top, experienced a great deal of subsidence. It's kind of a proxy for most of South Louisiana. It had a lot of subsidence in the mid-60s through around the mid-80s, and then it's kind of stabilized in the meantime. So if we just real quick, we're going to go from 1932, where in this area, this is the downthrown side of the fault, and this is the upthrown side of the fault. And what I want you to notice is that we're going to see some really rapid land loss at 1975, okay? And you've got a relative retention of land to the north, but you'll also notice that that's also downthrown to this second fault that's a little bit further to the north. And then by 1985, we've almost lost all of our land, and in 2009, it's fairly complete, except for a little distributary right here that has come out of the main part of the river. Okay, so what we're doing in this process is, first thing we're doing is finding out what 2Ds and 3Ds might be available to be used, and then we're compiling public information on where faults have been identified in the past, and then we're putting it all into an ArcGIS setup so that the fault locations can be compared to the transportation infrastructure network. And all of this is going to be something that really is going to have follow-up afterwards that will be more location-specific for infrastructure projects in the state. So this is a diagram I've included, and mostly to demonstrate that faulting in Louisiana has been extensively studied, but on the other hand, this isn't an accurate picture. Okay, one of the most important things to notice on here is look at the length of these things. These are 40, 50, sometimes probably more than that, miles in length. And another thing I wanted to show was we've got these 3 areas of focus. One up here by Lake Pontchartrain and the New Orleans Land Bridge. Down here, this is Golden Meadow, about right here, and we're traveling down to Fouchon, so we've got Golden Meadow, and then over west of there, near Montague, are the 3 focus areas that we have graduate students working. Incidentally, the little red circles are felt reports. So this was done for the Corps of Engineers by Woody Gagliano's group out of Baton Rouge, Coastal Environments. And we've got a published report that we've included in our study by Armstrong of 2014 down here, and it includes part of that area that we were just showing you with the marsh break. Now, 3D gives us a volume of data, okay? And I did not include the full animation of this, but what I wanted you to see was that we've got a fault that's been picked right here in this big cube of data, all right? And this is a horizon that's been mapped, and the horizon colors are indicating the upthrown and the downthrown side, and the hot colors are higher in elevation or really depth, shallower in depth, and this is deeper. And this, what we would do is fault right here, and we're going to project it up to the surface and end up being a trace. Now this is in the middle of the marsh. Okay, this is not so important for the type of work that Department of Transportation in Louisiana does, but we do have examples of it being in other places. So a growth fault is the type of fault we were talking about, and this is the study area from Armstrong. The growth faults here are shown as planes where red is shallow and green is deeper, and they're actually extending at an angle into the surface. And this is a 3D volume of several tens of square miles at least. And if we superimpose that area right here onto the Gagliano map, what we see is that the pink faults that were identified here as growth faults end up being much shorter segments, have a much, there's some basic similarities. We've got a fault here, we got something here, here. This one's kind of interesting because Armstrong is seeing one single fault or maybe 2 segments, but Gagliano's saw this segment and connected it differently. Okay, so they saw something different, but really the 3D is going to be a more accurate representation of what is actually going on, and then you go in and you go look at it in more detail. Let's see, this area over here was just simply not part of the 3D data set that she looked at. And so the idea is we have a lot of existing information about faulting in Louisiana, but it's inaccurate without really looking at the subsurface. You cannot assess a fault just looking at surface or near surface effects. So if we look a little bit more closely at some of the areas that are, have infrastructure, this map is showing DOTD transportation links, roads, and highways in South Louisiana. This is our study area, in this bounds right here. And on this map, we've just kind of taken all of the available 3Ds that are available for licensing and colored them in pink, and the areas where there are no 3Ds available are colored in yellow. So you can see that there's large areas that have no 3D, spotty areas where we don't have 3D, and then there's some areas that have a lot of 3D. Okay, and this one's really important down here by LA1. This map shows the same yellow areas that have no data, but 2D data, so just a line instead of a volume, are depicted on here. So the areas that you have a gap and yellow underneath, showing the gap, and the blue superimposed on top, those are the areas where you'd be limited to using 2D to be able to define anything. And notice again down here, we don't have a whole lot of yellow, but we do have some yellow in this important area up here where we've got Highway 11, Interstate, and Highway 90. So if we take a look at the Golden Meadow area, this is a published seismic line from Coulthard et al., 2008, and north is on the right, south is on the left. You can see that we've got a very large fault right here that goes down. This is probably, at least 15,000 feet, maybe 20,000 feet at this depth. And we've got a cluster of faults here that are making a graben right in the middle. And we've just taken his interpretation here, but we've talked about it, and we probably would work it just a little bit differently. But the idea is that you've got an area right in here where LA1 is, and going through Golden Meadow, that there's an area that for a long time, this is mid-Pleistocene, that's about 2 million years ago, so for a long time, this thing has been sinking right here in the middle. If we take a look at what sediment cores do, now this is just 500 feet right here, so you're seeing the surface up here, and 500 feet on this seismic line goes from about here to here. So this area up here on a conventional energy company type seismic line, we really don't get a lot of good data up there because they're concentrating on where the oil and gas is, when they're processing this data. But that's why it's a coupled, linked process to work with the 3Ds and then and then work on shallow interpretations or get data gathering once you have the deeper interpretation. So Amanda Johnston at UL with her Professor Ray Zhang are working on really doing a 3D interpretation all the way from Golden Meadow down to Leeville. And this is the projection of the faulting that she's done, and it's a work in progress, okay? So this is not her final project or final product at all, but it's close. And the point is that we've got LA1 going across here, and if there's, sustained problems, then there could be a reason for it. So, this is just emphasizing where it is, and I think this is the next phase of LA1. And, again, we've got faulting in the Golden Meadow area and some faulting down there with Leeville Salt Dome. If we go up here to another focus area where the land bridge is, here we don't have 3D except for over in this corner where we also have very highly dense 2D data. And again, we've got the fault that we noted at Highway 11 bridge. It's projected to continue all the way across Lake Pontchartrain and into Lake Bourne, where 2D high-res chirp data has been acquired to confirm what the 2D deep seismic had shown, but only in segments. So when we have 2D data, if you notice on here, we've got a solid line and a dashed line and a solid line. Those solid things connect where we had a line that went across, and we could tell that we had 5 different faults going across that line. But it's projecting when we're doing it. So we still could have some segmentation, but we don't have 3D data here to be able to confirm that. So finally, in conclusion, we would say that active faults are part of the subsurface. There's really no denying it. And limited access to the energy industry data because of licensing and really the purpose of it was for oil and gas has made it difficult to make the delineation of a true fault trace effective. However, through some donations that have been made to universities and some other efforts, this data has now been provided in certain areas, and it's a useful step in quickly assessing things. The interpretation of it is going to allow us to focus on other tests that would be follow-up geotechnical work, sediment borings, age-dated sediment layers, CPT profiles, and high-resolution seismic specific to an area so that one can most cost-effectively analyze what's going on. And a thorough fault assessment will only lead to a better assessment of what is happening in the surface deformation of transportation infrastructure. Thank you.